So what kind of torque adjustments are needed if you use something like a crow's foot on a torque wrench? So basically, what we run into is we run into these descriptive equations where we have the force where it's applied. This would be at the ratchet end. This would be at the pivot for the crow's foot, or the bolt pivot. So the input would be set for the torque wrench. That'd be the independent variable. And then for that, there'd be an application force and the distance to where the force is applied on the wrench. The question is, the independent variable we're looking for would be the torque at the crow's foot, which would be driven by the force where it's applied on the wrench, times the distance from where the force is applied on the wrench compared to the pivot point on the ratchet socket point, which would be here. And then we would add on the length of the crow's foot. Now the force, just doing the mathematics, we end up with that. The substitution, we can find the independent, or find the dependent variable from the dependent torque variable from the independent torque independent variable. And the equations boil down to the net length from where the force is applied to the pivot point on the crow's foot, or the new pivot point, we could say, divided by the same torque for the same distance where the force would be applied, as if the crow's foot did not exist. So then, just applying some numbers to this, if we set x as to 14, which is for the longer wrench, and the crow's foot is 0.75, and we have a shorter wrench or force application point, and that would be at 11 inches. The crow's foot still would be 0.75. That 0.75 is this point here, this point here. The application point of x would be from this point here to wherever we apply it here. We could apply it here too. We could apply it anywhere. Okay, but in this case, we're applying it to the center of the handle here. And so we end up with these equations for case 1 and case 2. In fact, this could be the same wrench, just applied at a different location on the wrench. And so what we end up with is we start to find that the independent variable and these independent variables, the torque at the crow's foot, is actually a function of the application point, and of course the length of the, I would say we could call it the secondary torque location, or the pivot point of the crow's foot in this case. So then we end up with these two equations here, x plus y, 14.07, 13.75 over 14, this one here, 11.75 over 11 for the two different application points, or two different lengths of wrenches. The mathematics for this particular cases gives 1.054 and 1.068, which tells us that this one would the torque would be an over torque of 5.4%, and this would be an over torque of 6.8%. So if we apply this 15 foot-pounds and we use the shorter application length, force application length, we end up with 1.68. So 15 foot-pounds would turn into be about 16 foot-pounds. What this tells us, though, is that there's a greater accuracy for a longer torque wrench if we're using an extension on it, and one of the, even with the same wrench, applying the force even further out on the handle, as opposed to choking up on the handle and applying it up further up, simply by reduction of the force, the compensation by the leverage arm, allowing the force to be reduced and effectively improving the ratio from the application versus the secondary, what we call the secondary torque length. Okay, so the recommendation would be for these is use as long of a cantilevered arm as you can if you want to have it close, or otherwise if you're using a very short or the ratio's very close, the X versus the X to Y ratio is close. If Y is very close to, is not much smaller than X, if Y is not much smaller than X, then you would want to do the calculations to make sure that the accuracy was here. If it's much longer, if X is much longer than Y, it could probably be neglected. That's all.